After studying this module, you shall be able to learn about the osmometry technique for determination of molar mass of polymers, understand the importance of second virial coefficient in case of polymer solutions, mathematically prove that osmosis technique gives number average molar mass of a polymer. Macromolecules, also known as polymers, are formed by the covalent linkages between many repeating small molecules known as monomers. In the preparation of the polymer from monomer units, the polymerization reactions proceed through different extents of reaction. Thus, this results in polydispersity in molar masses. As a result, macromolecules do not have a unique molar mass. Depending upon the method by which the macromolecule is produced, same molecule may have different molar mass. Hence, for macromolecules, the concept of average of molar mass is used. In order to describe the distribution of molar masses, the following averages are commonly used. Number 1 is the number average molar mass Mn bar given by summation Ni Mi by summation Ni as our equation 1, where Ni is the number of molecules each having molar mass Mi. Number 2 is the mass average molar mass Mw bar equals to summation Wi into Mi as equation 2, where Wi is the mass fraction and Mi is the molar mass. Number 3, Z average molar mass Mz bar, this is equal to summation Ni Mi cube by summation Ni Mi square as equation 3. Number 4 is the viscosity average molar mass Mv bar equals to summation Ni Mi to the power a plus 1 divided by summation Ni Mi whole to the power 1 by a. This is our equation 4. Now, we shall see the measurement of molar mass and size. The molar mass of polymers can be determined by a variety of physical and chemical methods such as bifunctional group analysis, by measuring the colligative properties, by light scattering method, by ultracentrifugation, or by viscosity measurement of dilute solutions. All these methods except the viscosity method are in principle absolute. That is, molar mass can be calculated without reference to calibration by some other method. However, dilute solution viscosity measurement method does not involve direct estimation of molar mass. Its value lies in the simplicity of the technique and the fact that its results can be related empirically to molar masses for many systems. Thus, dilute solution viscosity methods yields viscosity average molar mass, which is not an absolute value, but a relative mass based on prior calibration with known molar mass for the same polymer solvent temperature conditions. With the exception of some types of N-group analysis, all molar mass methods require solubility of the polymer, and all involve extrapolation to infinite dilution or operation in a theta solvent in which ideal solution behavior is attained. Table lists the different molar masses described along with the experimental methods to determine the various average molar masses. For example, we have number average molar mass given by summation Ni Mi by summation Ni. It can be determined by methods such as osmotic pressure and other colligative properties and fluid group analysis. Mw bar is given by summation Wi Mi can be determined by light scattering sedimentation velocity. Mz bar given by summation Ni Mi cube by summation Ni Mi square can be determined by sedimentation equilibrium, and Mv bar given by summation Ni mi to the power a plus 1 divided by summation Ni mi whole to the power 1 by a can be determined by the intrinsic viscosity measurements. Now, we shall have a look at the colligative property measurement. The relations between the colligative properties and molar masses for infinitely dilute solutions lay upon the fact that the activity of the solute becomes equal to its mole fraction as the solution concentration becomes sufficiently small. The activity of the solvent must equal to its mole fraction under these conditions, and follows that the depression of the activity of the solvent by a solute is equal to mole fraction of the solute. The colligative property methods used are lowering of vapor pressure, elevation of boiling point, that is the Vidya-mitra, depression in freezing point, that is the cryoscopy, and the osmotic pressure measurements, that is the osmometry. A colligative property measures the number of particles in solution. Therefore, colligative property measurement of a polymer yields number average molar mass. Number average molar mass can be calculated by using a dilute solution of a polymer through any of the methods from Vidya-mitra, cryoscopic and osmometry. Direct measurement of lowering of vapor pressure for dilute polymer solutions is not precise and gives uncertain results. However, vapor phase osmometry is an indirect method based on Clapeyron equation, using which the vapor pressure lowering of a polymer solution at equilibrium can be related to the temperature difference that is comparable to or of the same order of magnitude as those observed in cryoscopy and Vidya-mitra. These methods require calibration with low molar mass standards as they may produce reliable results for polymer with molar masses less than 30,000. The work equations for Vidya-metric, cryoscopic and osmometric measurements are as follows. Delta Tb by C limit x tending 0 is equal to RT square by rho delta HF into 1 by Mn as equation 5. Delta Tf by C x tending 0 equals to RT square by rho delta HF into 1 by Mn as equation 6, and pi by C limit of x tending 0 equals to RT by Mn as our equation 7, where delta Tb is the elevation in boiling point, delta Tf is the depression in freezing point, pi is the osmotic pressure, rho is the density of the solvent, and C is the concentration of the solute in grams per milliliters or grams per centimeter cube. Delta HV and delta HF are the enthalpies of vaporization and fusion respectively of the solvent per gram. The number average molar mass Mn bar has been introduced in equation 5, 6 and 7 in order to make these equations applicable to polydisperse solutes. Majorly, osmotic pressure measurements are used for studying the macromolecules because osmotic changes are larger than other changes in other colligative properties. This is due to the fact that even a very small concentration of the solution produces a fairly large magnitude of osmotic pressure, while at this small concentration the values of other colligative properties such as boiling point elevation and freezing point depression are too small to be experimentally determined. Thus, osmometry technique is more useful and thus is more widely used than any other colligative techniques for polymer systems. Now, we shall see the process of osmosis and osmotic pressure. When a solution and pure solvent are separated with the help of a semi-permeable membrane, diffusion of solvent molecules takes place from the side of the pure solvent to solution. This flow of solvent molecules from a region of their higher concentration, that is the pure solvent, to a region of their low concentration, that is solution, is known as osmosis. As a result of osmosis, the meniscus of the solution tube rises, whereas that of the pure solvent falls. until equilibrium is reached when the meniscus of the solution tube does not rise further. At this stage, the excessive hydrostatic pressure created on the solution side exactly balances the tendency of the solvent molecules to pass through the membrane as shown in figure. This excessive hydrostatic pressure is known as the osmotic pressure of the solution and is represented by the symbol pi. Thus, osmotic pressure arises because of the equilibrium between the solvent in solution and the pure liquid solvent. Figure depicts the phenomena of osmosis and the generation of osmotic pressure. The osmotic pressure of a solution depends on its concentration, that is, larger the concentration, larger will be the osmotic pressure. The relationship of osmotic pressure with the concentration of the solution can be derived thermodynamically. In this module, we will not consider the entire derivation, but we will only use the following results. Pi into V star Lm equals to minus RT ln chi 1, where V star Lm is the molar volume of the solvent, chi 1 is the amount fraction of the solvent in the solution. We will simplify equation 8 for a dilute solution using the following approximations. Number 1, since the solution is dilute, therefore chi 2, that is the amount fraction of the solute, is much less than 1. Therefore, the term ln chi 1 can be approximated as ln into 1 minus chi 2, which can be further approximated as minus chi 2. This is our equation 9. Second, the amount fraction of solute is given by chi 2 equals to N2 by N1 plus N2, which can be written as N2 by N1. This is our equation 10. 3. For a solution, the total volume V can be written in terms of the partial molar volumes following the additivity rule as V equals to N1 V1 plus N2 V2, where V1 is the partial molar volume of the solvent and V2 is the partial molar volume of the solute. Thus, for a dilute solution, we can make the following assumptions. 1. Partial molar volume of the solvent in the solution is same as that of the pure solvent, that is, V1 is equals to V star Lm. 2. The factor N2 V2 is much less than N1 V1. Since N2 is much less than N1 and can be neglected. Thus, we have V approximately equal to N1 V1, which is further equal to N1 V star Lm. This is our equation 11. Substituting equations 9, 10, 11 in equation 8, we get V upon N1 into pi equals to minus RT into minus chi 2 equals to RT chi 2, or we have V upon N1 into pi is equal to RT N2 by N1, or V pi is equal to N2 RT, or pi is equals to N2 by V into RT, which is equal to CRT. This is our equation 12, where pi is the osmotic pressure, C is the molar concentration of solute in the solvent, R is the gas constant and T is the temperature. Equation 12 is known as the Van 't Hoff equation for determining osmotic pressure of the solution. This equation is exactly identical to the ideal gas equation, that is PV equals to nRT. This is our equation 13. Except that pi replaces the gas pressure P, this resemblance indicates that the solute molecules are dispersed in the solvent in the similar way as the gas molecules are dispersed in the empty space. Thus, the solute is analogous to the gas molecules and the solvent is analogous to the empty space between the gas molecules. Now, we shall see the expression of osmotic pressure for polymer solution. We have already studied that osmotic pressure measurement is method primarily used in the determination of the molar masses of substances, which have either very low solubility or very high molar masses such as proteins or polymers. The Van 't Hoff equation number 12 is valid either only at infinite dilution or to a very dilute solution where the solute-solute interaction is negligible. Thus, this equation might not be applicable to a substance of high molar mass at concentrations which are employed for experimental methods. Moreover, a polymer solution does not behave as an ideal solution because there is large difference in the molar volumes of the polymeric solute and that of the low molar mass solvent. Therefore, we take this fact into consideration and apply the following conditions to equation 8. That is, firstly, we program the expansion of logarithm in expression 9 as ln chi 1 equals to ln of 1 minus chi 2, which can be further written as minus of chi 2 plus chi 2 square by 2 plus chi 2 cube by 3 plus so on as our equation 14. And thus expression 8 can be expressed as pi v star lm equals to RT into chi 2 plus p prime chi 2 square by 2 plus c prime chi 2 cube by 3 plus so on as our equation 15, where b prime is the second virial coefficient, c prime is the third virial coefficient. If the concentration of the solution is expressed in mass of solute per unit volume of solution, then chi 2 can be approximately written as N2 by N1. This is our equation 16. Also, N2 is equal to M2 by M2 and N1 is equals to V by V star Lm as our equation 17. Using equation 17 and equation 11, we have chi 2 equals to M2 by capital M2 divided by V star Lm equals to M2 by V into V star Lm by M2, which is further written as C2 V star Lm by M2 as our equation 18. Substituting equation 18 and equation 15, we get pi V star Lm equals to RT into C2 V star Lm divided by M2 plus half p prime C2 V star Lm by M2 square plus so on, or pi by C2 RT equals to 1 by M2 plus 1 by 2 into p prime V star Lm by M2 square into C2 plus so on, which can be further written as equal to 1 by M2 plus B times C2 plus so on as our equation 19. The higher terms are insignificant. Thus, retaining only the first two terms on the right hand side, we get pi upon C2 RT equals to 1 by M2 plus B times C2 as our equation 20. Equation 20 predicts that for a non-ideal solution, the plot of pi upon C2 RT and C2 is linear. The slope obtained from this graph is equal to the second virial coefficient B prime and its intercept is equal to the reciprocal of the molar mass M2 of the solute. Figure shows the plot of pi by C2, that is the reduced osmotic pressure, versus C2. We can also plot pi by C2 reduced osmotic pressure versus C2, an equation as shown as figure from this graph, which when extrapolated to C2 equals to 0 gives slope equals to B prime RT and intercept equals to RT by M2, that is pi by C2 limit C2 tending to 0 is equal to RT by M2. Now we shall see the discussion of the second virial coefficient B prime. The virial coefficients are determined empirically for a given solute-solvent system. The second virial coefficient, that is B prime, represents the interaction of a single solute particle with the solvent, while the higher order virial coefficients are associated with correspondingly larger number of solute particle clusters interacting with the solvent. Thus, second virial coefficient is a measure of interparticle interactions and hence is temperature dependent. Figure shows the plot of reduced osmotic pressure pi by C2 versus C2 at different temperatures. The temperature at which for a given polymer solvent pair the polymer exists in unperturbed state is termed as the theta temperature. This is also the temperature at which the second virial coefficient becomes 0. In figure T2 is the theta temperature. This temperature is also called the critical solution temperature for a polymer of infinite molar mass. Since B prime is temperature dependent, therefore, for each polymer solvent pair, there exists a unique temperature at which B prime is 0. At theta temperature, there exists no interactions between different polymer chains. The polymer solution behaves as an ideal solution at this temperature. Above theta temperature, that is T1, as shown in figure, there is a positive deviation, and a positive value of B prime indicates that the polymer is insoluble in the solvent. While below the theta temperature, there is a negative deviation shown by temperature T3 in figure, and the polymer chain segments will attract one another, and eventually the phase separation will occur. Moreover, a negative value of B prime is indicative of a good solvent, that is, the polymer will be highly soluble in the given solvent due to favorable polymer-solvent intermolecular interactions. Now, we shall see the mathematical proof that osmotic pressure gives the number average molar mass. The osmotic pressure measurements leads to number average molar mass because osmotic pressure is a colligative property which depends on the number of molecules of the polymer and not on their masses. All the molecules, whether heavy or light, make equal contribution. Mathematically, since osmotic pressure pi consists additively of the partial osmotic pressures pi 1, pi 2, pi 3 and so on for the molecules of different degrees of polymerization 1, 2, 3 and so on. Thus, from equation 12, we have pi equals to pi 1 plus pi 2 plus pi 3 plus so on, which is further can be written as pi equals to C1 RT by M1 plus C2 R2 by M2 plus C3 RT by M3 plus so on. The same holds for the total concentration, that C is equals to C1 plus C2 plus C3 plus so on. Thus, the osmotic average molar mass can be written as M bar osmotic is equal to C1 plus C2 plus C3 plus so on into RT divided by pi 1 plus pi 2 plus pi 3 plus so on, which can be further written as C1 plus C2 plus C3 by RT divided by RT into C1 by M1 plus C2 by M2 plus C3 by M3 plus so on. Or this is equal to summation Ci divided by summation Ci divided by summation Mi, which is equals to Mn bar. Hence, the expression proves that osmotic pressure yields number average molar mass Mn bar. Now, we shall summarize what we have learned in this module. Osmometry technique for determination of molar mass of polymers. Osmotic pressure of a solution is given by the Van 't Hoff equation, that is pi equals to N2 by V into RT, which is equal to CRT. Polymer solution is a non-ideal solution. Thus, osmotic pressure for a polymer solution is given by pi upon C2RT equals to 1 by M2 plus B into C2, where P is the second virial coefficient and M2 is the molar mass of the polymer. Osmometry techniques provides number average molar mass, that is Mn bar, which is equal to summation Ni Mi divided by summation Ni.